Hello everybody. In this video we'll be covering one of the sections in Chapter 2 of our textbook Introductory Chemistry by Tro. This chapter is titled Measurement and Problem Solving. So in this video I want to talk a little bit about density, and this is our first quantity that we're going to be talking about that's a calculated quantity. It's not something that we measure directly, but something that we wind up calculating from values that we actually do measure. So mass is related to, or density is related to the mass and the volume. The mass and the volume are two main characteristics of matter. They're directly measurable. But they cannot be used to identify the type of matter that something is, okay? And the reason for this is that they're dependent upon the size. So if I have more of something, I'm going to have more mass, I'm going to have more volume. And if I have less of it, I'm going to have less mass and I'm going to have less volume. I can't determine based just on mass and volume what something is. So an example of this is if you are given a large glass containing 100 grams of clear colorless liquid and a small glass containing 25 grams of clear colorless liquid, can you determine if they're both the same stuff? You really can't, right? You don't know. You're not given enough information here to determine the identity or even whether they're the exact same liquid. Density, however, is a unique type, is unique to a type of matter. And what density is it's the mass divided by the volume of a substance. Now you will have different substances that have very similar densities, but if you had enough precision, if you measured the mass carefully enough and the volume carefully enough, and you had a pure substance, you would be able to figure out what it is based on the density. So here we have some data. We have different samples of brass, and we have their mass in gram and their volume in cubic centimeters or milliliters. Now, if I calculate the density for each one of these, so I'm going to divide this mass in grams by this volume in cubic centimeters, I get the density in grams per cubic centimeter. That's going to be the unit for our density. I'm going to see that I see some variation. And this is exactly what we've been talking about so far. Given the level of precision that we made these measurements and the uncertainty in them, we're getting slightly different values with slightly different significant figures for each one of these values. But they're all roughly about the same, right? They're all somewhere between 8.3 and 8.4 grams per cubic centimeter. So we can say that we're narrowing in on what that density is. One thing that we can do is actually use a technique called linear regression, where we're now taking every single one of those points that we had before, with the volume on the x-axis here and the mass on the y-axis. We can plot those out, and we can use a mathematical technique called linear regression. We see that we get a straight line. The slope of this line is going to be the rise over the run, or the mass over the volume, and we're able to see that we get 8.38. In this case it would have been grams per cubic centimeter as our density. So this is a technique that we can use to take that raw data and narrow in on what the actual value is for our density. The real usefulness for this is that now we can kind of extrapolate or interpolate values in between. So if I give you the volume, for instance, now you can come up from that volume point to the line over here and tell me what that mass is going to be. So this is a really powerful technique that we use in the lab. Let's talk about some of the value, some of the things, like do some thought experiments around density. For equal volume, the denser object has the larger mass. Okay, so if two things occupy the same amount of space, something that's more dense is going to have more mass to it. For equal masses, the denser object has a smaller volume. Okay, so if you have something that's very, very dense, it's going to accumulate mass very quickly as you add volume to it, So a smaller volume is going to have the same mass as something that's less dense. Heating objects causes objects to expand. This does not affect their mass, but it will affect their density, right? If you're increasing the volume but not changing their mass, because we have conservation of mass, you're going to have a lower density. This, for instance, is the reason that hot air balloons float. You heat the air inside of the balloon, it causes it to expand, it has less density, it's then able to float on the cooler air on the outside of it. In a heterogeneous mixture, this is a mixture where everything is not the same or consistent throughout, the denser objects sink. Okay, so this is why the hot air balloons rise. Okay, so it's making it less dense, it's able to rise. It's the reason why a rock will sink in water. It's less dense than the water around it. Let's take a look at this problem here. Platinum has become a very popular metal for fine jewelry. A man gives a woman an engagement ring and tells her that it is made of platinum. Noting that the ring felt a little light, the woman decides to perform a test to determine if the ring's density before giving him an answer about the marriage. She places the ring on a balance and finds it has a mass of 5.84 grams. She then finds that the ring displaces 0.556 cubic centimeters of water. Is the ring made of platinum? And we know that the density of platinum is 21.4 grams per cubic centimeter. So we have our problem restated up here. Again, we start off with our known quantities here. We know that we have 5.84 grams and that the ring is displacing 0.556 cubic centimeters. Our question is, what is the density? And we have an equation for density. The mass divided by the volume is going to equal the density. Our solution map is that we're going to take our mass and our volume, and we're going to find the density using our equation. We can look at that pictorially here. We're going to take mass and volume. We're going to apply our equation, and we're going to get out a density. Taking the mass of 5.84 grams and dividing it by 0.556 cubic centimeters, our volume, we see that this ring has a density of 10.5 grams per cubic centimeter, meaning that the ring is in fact not platinum, which may or may not be a reason to not marry somebody. So let's take a look at density as a conversion factor. We can use density as a conversion factor between mass and volume. Okay, the density of water, H2O, is equal to 1 gram per milliliter. Therefore, that's what these three dots right here mean. 1 gram of water is equal to 1 milliliter of water. The density of lead is equal to 11.3 grams per cubic centimeter. Therefore, 11.3 grams of lead is equal to 1 cubic centimeter of lead. Now we have our statements like we had before using conversion factors, and we can start to make our different conversion factors between them. So now we're asking, how much does 4 cubic centimeters of lead weigh? So if we have 4 cubic centimeters of lead, we can use our conversion factor based on this statement to convert this into mass, where we have 11.3 grams per lead for every 1 cubic centimeter, and we'll know that that volume of lead is equal to 45 grams of lead. We'll finish off our section on density by looking at a practice problem here. What volume does 100 grams of marble occupy? If we know that the density is equal to 4.00 grams per cubic centimeter, or 4.00 grams divided by every 1 cubic centimeter. I'll give you a moment to work this out. So if we use our density as a conversion factor, we can do the reciprocal of this, or, reversing the numerator denominator of our density in order to cancel our grams and arrive at the fact that 100 grams is equal to 25.0 cubic centimeters.